Hello everybody. Let us look at the JEE level questions in this video. Let's begin with the first question. Variation of electrostatic potential along the x direction is shown in the figure. The correct statement about the electric field is. Now we know that the electric field E is given by minus dV by dx, which basically means that the electric field is directed in a direction where the potential decreases the most. Look at if you look at the point C, there the electric field is reducing the steepest. So the electric field must be in the positive x direction. I think that's option 4. The x component at point C is along positive x direction. That's the correct answer. Let's go further. Look at the second question. Two spherical conductors of radii R1 and R2 are separated by a distance much larger than the radius of either sphere. The spheres are connected by a conducting wire as shown in the figure. The charges on the spheres in equilibrium are Q1 and Q2 respectively. What is the ratio of field strength at the surface of the spheres? Now we know that Q1 divided by R1 would be equal to Q2 divided by R2 for the potentials to be equal. Because they are connected by a connecting wire, their potentials must be equal. Now potential is 1 by 4 pi epsilon naught Q by R. So 1 by 4 pi epsilon naught has been cancelled. So I write just Q1 by R1 equal to Q2 by R2. And also, if you just figure out what is R1 divided by R2, R1 divided by R2 would simply be Q1 divided by Q2. When that is the situation, we have to find the ratio of electric fields, and we know that the electric field is directly proportional to charge and is inversely proportional to square of the radius. So we have E1 divided by E2, dear friends, equal to R2 divided by R1 the whole square multiplied by Q1 divided by Q2. But from the potential equation, Q1 by Q2 can be written as R1 by R2. So out of R2 square and R1 square, one R1 and one R2 would get cancelled. You will have R2 divided by R1. So that is option number 1. So let's go further. Solve question number 3. N charged drops, each of radius r and charge q, coalesce to form a big drop of radius capital R and charge capital Q. If V is the electric potential and E is the electric field on the surface of the drop, then which of the statements is true? Let us look at the potential first. Now, the potential can be calculated this way. First of all, we need to know the radius of the big drop. Now, let's assume the radius of the small drop is R and the radius of the big drop is capital R. N small drops are combining to form this one big drop. So N into volume of the smaller drop is 4 by 3 pi small r cube. It's equal to the volume of the bigger drop, which is 4 by 3 pi capital R cube. 4 by 3 pi and 4 by 3 pi gets cancelled. We have capital R being equal to n to the power of 1 by 3 times small r, right? Now we have the equation for potential. Potential is 1 by 4 pi epsilon naught. The total charge is Q and the total radius is R. Let us substitute it let's substitute for capital Q. Capital Q is n times small q and capital R is n power 1 by 3 times small r. So that becomes n to the power of 2 by 3 times 1 by 4 pi epsilon naught Q divided by R, which is basically the potential of the smaller drop. So the big drop's potential is n power 2 by 3 times potential of the small drop, which is option 4. Option 4 is the correct answer. Let's hop to question number 4. A small sphere with mass 1.2 gram hangs by a thread between the two parallel vertical plates 5 centimeter apart. The charge on the sphere has been given. Potential difference has to be found. Now, if you just look at it, the electrostatic force, which is Q into E, would act in that direction, and M into G would act in this direction. The tension T can be resolved into two components. This is T cos 37 degree, and to this side it is T sin 37 degree. Now, T sin 37 degree balances QE, whereas T cos 37 degree balances mg. If you divide both of them, you have tan 37 degree, which is equal to QE divided by mg. Tan 37, by the way, can be figured out. because we have the right angle triangle, 345 triangle. In a 345 triangle, if you write 37 degree, the opposite side is 3 and the adjacent side is 4. So it's basically 3 by 4. The electric field can be written as V divided by D, where D is the distance between the two plates of this capacitor, if you want to call it so. MGD is all you will have. Now, you want to find the potential difference. V is going to be 3 mgd divided by 4q. All the quantities are given. When you substitute for these quantities, for example, mass is 1.2 gram and charge is 9 into 10 power minus 6, D is 5 centimeter, G is 10. Substitute and you would get 50 volt. Option 3 is the correct answer. Let us go further to question number 5. This is a question which allows you to think about potentials. Let's begin with this question number 5. A conducting sphere A of radius small a with a charge q is placed concentrically inside shell B of radius b. B is earth and C is the common center of A and B. Study the following statements. Let's read the statements. Potential at a distance r from C, where r is less than a but greater than r is greater than a but less than b, is 1 by 4 pi epsilon naught q by r. Let's try to figure it out. We have the potential. We are trying to find the potential at a point there, which is greater than A and less than B. Let's write down what is the potential due to A. Potential due to A is 1 by 4 pi epsilon naught q divided by R. And potential due to B would be 1 by 4 pi epsilon naught minus q divided by B, because it has to induce an equal amount of negative charge on the inner surface. So having said that, we have potential at that distance. Potential at that distance, VR, would be equal to 1 by 4 pi epsilon naught q by R minus q divided by B. If you pull out q as a common factor, it would be q by 4 pi epsilon naught 1 by R minus 1 by B. So that doesn't match with option 1. So that's not the correct answer. Let's look at the second statement. Second statement says that the potential difference between A and B is 1 by 4 pi epsilon naught q into 1 by A minus 1 by B. Let us reason this out. We have delta V equal to, anyway, we know the potential at A and potential at B. We are talking about the potential at the surface of A and B. So then R would become equal to A. Then the answer, manipulating this previous equation, q by 4 pi epsilon naught 1 by A minus 1 by B you will have, which is actually correct. And third one, let's find out what the third one says. The potential at R at a distance from C is 1 by 4 pi epsilon naught q into 1 by R minus 1 by B. That's exactly the equation that we have got in this case. So we are looking at this question, and 2 and 3 statements are correct. So you can say only 2 and 3 are correct. Option 2 is the correct answer. Having understood this, let's go further. Question number 6 here. The figure shows 3 circular arcs, each of radius r and total charge as indicated. The net electrostatic potential at the center of curvature is, we are supposed to find the potential at the center of the curvature. If that is the case, we know that the potential at the center is given by 1 by 4 pi epsilon naught total charge divided by the radius. That's the expression for potential at the center of a ring. Now the total charge is going to be q plus 3q, making it 4q, minus 2q, making the sum 2q. So I have 1 by 4 pi epsilon naught. Total charge is 2q divided by r. So it would be q divided by 2 pi epsilon naught r, which is basically option 1. Let's go further and talk about the seventh question. A unit positive charge of mass m is projected with a velocity v inside the tunnel as shown. The tunnel has been made inside a uniformly charged non-conducting sphere. The minimum velocity with which the point charge should be projected such that it can reach the opposite end of the tunnel is equal to. So we are supposed to calculate the velocity with which it reaches, with velocity with which it must be projected for it to reach the other surface of the tunnel. Let's do this. Well, if it reaches this point, the center, then it will definitely go to the other side, because it's the potential at this place and potential at this place are equal, but this potential is higher. So we will have to figure out how much is the velocity. But anyway, total energy remains conserved. Delta K plus delta U would always sum up to 0. Anyway, initial kinetic energy, final kinetic energy is 0 minus, so final kinetic energy is 0, and the initial kinetic energy is half mv square, and plus the charge into potential difference, Vf minus Vi, is all you will have, equal to 0. Now question is, what is Vf? Vf would be the final potential, which is the potential at the surface divided by 2 into 3 minus r square divided by r square. Now if you write it in terms of volume charge density, it would be rho r square divided by 6 epsilon naught multiplied by 3 minus r square divided by r square. Well, now we know that small r, given in the question, that's r by 2. So small r is r by 2. Let me substitute that as r by 2. The final potential Vf would now become equal to 11 rho r square divided by 24 epsilon naught. And the initial potential at the surface would be rho r square divided by 3 epsilon naught. Going further, now we can calculate the kinetic energy. The kinetic energy half mv square, that is to be supplied, would be equal to, Q is anyway 1 microcoulomb. And the final potential is 11 rho r square divided by 24 epsilon naught minus rho r square divided by 3 epsilon naught, giving you rho r square divided by 8 epsilon naught. Now if you calculate the velocity from this, velocity would be rho r square divided by 4m epsilon naught power 1 by 2, which means it's under the root. Let us find out which option that is. Looks like rho r square divided by 4m epsilon naught power 1 by 2 is option 1. So that's the correct answer. Let's go further. Next question we have, question number 8. A graph of x component of electric field as a function of x in the region of space is shown in the figure. The x and z components of electric field are 0. The y and z component of electric fields are 0 in this region. If the electric potential is 10 volt at the origin, then potential at x equal to 2 meter would be. Let's figure out. Now we have the definition of electric potential in terms of electric field, which is VB minus VA is negative of E dot dx, right? Which is basically the negative of the area under the graph. So VB minus 10 would be equal to half into 2 into minus 20, which is equal to 20. So because at the origin it's already 10 volt, this is a 20 volt increment. So the total potential at B would become equal to x equal to 2 basically. 30 volt it would become. So 10 plus 20 would be 30. Option 4 is the correct answer. Let's go further and do question number 9. In an electric field shown in the figure, 3 equipotential surfaces are shown. If a function of electric field E is 2x square volt per meter is given, and if V2 minus V1 and V2 minus V3, the V1 minus V2 and V2 minus V3, then we have. Do you see that the same potential drop will keep occurring for smaller and smaller distances as and when you go further? And that's because it's an exponential function. The electric field increases as x square. So smaller, the same potential drop will occur for smaller and smaller distances, which basically comes to brings us to a conclusion saying x1 is greater than x2. That is option 2. So option 2 is the correct answer. Let's go further to question number 10. A positive charge Q1 is located to the left of a negative charge minus Q2 on a line joining through the two charges. There are two places where the total potential is 0. The reference is assumed to be at infinity, which means the potential at infinity is 0. The first place between the charges is 4 centimeter to the left of the negative charge. Second plate is 7 centimeter to the right of the negative charge. If Q2 is minus 12 coulomb, what is the value of Q1? Let's try to visualize this scenario. There is charge Q1 and then there is charge Q2. The distance between the place where the potential becomes 0 is 4 centimeter from here and 7 centimeter from there. If you just divide, if you look at why the potential is 0, you would simply say the sum of potential due to Q1 and potential due to minus Q2 would simply be 0, which means in magnitude both the potentials would be equal. Writing it, assuming that the distance between the two charges is x, you can write Q1 minus 4 is equal to Q by 4, Q2 by 4, because the potentials must be equal. And for 7 centimeter scenario, and the second scenario, this scenario, you can write Q1 divided by x plus 7 being equal to Q2 divided by 7. Then because we have Q1 by Q2 on both places, you can equate Q1 by Q2 on both places. You will have x minus 4 divided by 4 would be equal to x plus 7 divided by 7. Then automatically x would become equal to 56 by 3 after cross multiplication and simplification. Now we know that Q1 divided by Q2 is x plus 7 divided by 7. So in place of x you can substitute 56 by 3 and then you have the answer for Q1. Q2 is anyway given to you. It's going to be 11 divided by 3. Q2 is anyway given to you. Q2 is 12. So 1s are 4s are. So the answer would be 44 microcoulomb. Option 1 is the correct answer. Let's go further. Do question number 11. The plates of a parallel plate capacitor are charged up to 100 volt. Now, after removing battery, a 2 mm thick plate is inserted between the plates. Then, to maintain the same potential difference, the distance between the two plates of the capacitor are increased by 1.6 mm. The dielectric constant of the plate is, so we've got to find the dielectric constant of the plate. Initially, the voltage to which the plates are charged to the potential difference is 100. And the voltage across the plates of the capacitor can be written as sigma by epsilon naught into D. This equation is seen while deriving the expression for capacitance. So obviously we can go ahead and use that. This is the story of capacitor when it is placed in air. When you put a medium, and you pull the plates apart, the capacitor becomes partially filled, and for such the voltage would become sigma by epsilon naught into D minus T plus T divided by K. That's the expression for voltage between the two plates of the capacitor when the plates of the capacitor are partially filled. Having said that, we have the final potential because you are separating the two plates out in order to make the potentials the same. We will have a D plus D minus T plus T by K. Now, because this potential and the potential in air are both equal, you can just substitute, you can just equate both of them. Then you will have a sigma divided by epsilon naught into D becoming equal to sigma divided by epsilon naught into D plus D prime minus T plus T by K. On simplification, you get K equal to T divided by T minus D prime. Now, T is 2 divided by 2 minus 1.6, that would give you 5. So the dielectric constant that was initially put has a value 5. Let's go further and discuss question number 12. In this arrangement, we have C1 in series with this combination, and in the combination C2 and C3 are in parallel. So you can say that the charge on charge on C1, which is Q1, is equal to the combined charge on the parallel capacitors, which is Q2 plus Q3. And similarly, the total voltage is obtained by simply adding V1 and V2 or V1 and V3. V1 plus V2 is there, so we go ahead with option C. That's basic knowledge about capacitors being in series and parallel. Let's go further. Solve question number 13. An uncharged parallel plate capacitor having dielectric of dielectric constant K is connected to a similar air-cored parallel capacitor charged to a potential V0. The two share the charge and the common potential becomes V. The dielectric constant K is. We are supposed to figure out the dielectric constant. Now anyway, the air core capacitor is charged to V0, not the one with the dielectric. So we know that the common potential is found as C1 V1 plus C2 V2 divided by C1 plus C2. Let's use that formula now. C1 V1 can be C into V0. Anyway, C2 V2 would be 0 because the voltage of the second capacitor is 0. This is the air core capacitor. The capacitance is C. The other capacitor is a similar capacitor with a dielectric constant K. So it will become Kc. Let us pull out C as a common factor. It will become K plus 1. C and C would get cancelled. We have V equal to V0 into K plus 1. So if you cross multiply, this will be K into V plus V, or maybe we will just find K. K plus 1 would be equal to V0 divided by V, or K would become V0 divided by V minus 1. I think we have that option, V0 divided by V minus 1. It's option 1. That's the correct answer. Anyway, we've answered question number 13. Let's go further and answer question number 14. A, B, C, D, E and F are conducting plates each of area A, and any two consecutive plates are separated by a distance D. The net electrostatic energy stored in the system after which S is closed is. I mean, this is a very tricky arrangement, but the point is A and C are at the same potential. That means these things don't even form a capacitor. Same is the case with D, E and F. They are at the same potential, so they don't even form a capacitor. When you close switch S, there is going to be a potential difference of V volt across E and F. You are supposed to find the potential energy of the system, which is half CV square. C is anyway epsilon naught A divided by D. The only capacitor that you have to take is the capacitance between E and F, because everything else doesn't even form a capacitor, because for formation of a capacitor you must have potential difference, and this arrangement except for E and F there is no potential difference anywhere else. So what is the potential energy now? It is epsilon naught A V square divided by 2D. Epsilon naught A V square by 2D matches with option C. Let's go further and do question number 15. In the given arrangement of capacitors, 6 microcoulomb is added to point A. So this point gets a charge of 6 microcoulomb. Find the charge on the upper capacitor. Well, we have to find the charge on the upper capacitor. We don't know the voltage here, but at these places the voltage is 0. You can simply use the voltage at this place to be some V. So you must get the same voltage when you divide the charge with the capacitance, right? You know that C is equal to Q divided by V. V needs to be obtained, then Q by C. That is the voltage at this point. Let's figure that out. Let's assume the voltage at that point is K. So we have Q1 divided by 1. It's the same voltage as Q2 divided by 2. It's the same voltage as Q3 divided by 3. This is one fact. Let's call that voltage K. Now we also have another fact. Other fact is Q1 plus Q2 plus Q3, which is the charge sitting on each of the capacitors combined. That would be equal to 6, because the question says 6 microcoulomb has been added. Now you solve both of these equations and you would obtain K equal to 1. Once we know that K is equal to 1, we have to find Q3, which is the charge on the 3 microfarad capacitor. Q3 would become equal to K, which is 1 multiplied by 3. So the answer would be 3 microcoulomb. 3 microcoulomb is option 1. So let's do the rest of the questions in the following video. Thank you so much.